Hi, thanks for tuning in to Research Lab X Research Primer Series, Episode 5, Statistical Analysis is in the Systematic Review and Meta-Analysis. Hi, I'm Dr. Oscar Wong. In the previous video, we have covered an overview of the fundamental concept of systematic review and meta-analysis. In this video, we'll build upon that foundation and delve deeper into the statistical analysis and presentation of results. Specifically, we'll focus on important topics such as the use of forest plot to visually represent a result, considerations for the units of analysis, techniques for combining effect size, different types of meta-analysis including fixed and random effect models, how to conduct subgroup analysis, as well as how to perform a sensitivity analysis. By exploring this area, you gain a more comprehensive understanding on how to conduct and interpret a robust meta-analysis. So, there are several software options available for conducting meta-analysis, and here's an overview of the three commonly used software. First, we have Riefman, which is a widely used software developed by Cochrane Collaboration specifically for conducting systematic review and meta-analysis. It's a free tool that provides a user-friendly interface, making it accessible to researchers with no coding experience. Riefman allows users to input study data, perform statistical analysis, creating forest plot, and generating summary tables. Next, we have R. R is a powerful and flexible programming language commonly used for statistical analysis and data visualization. It offers a wide range of packages and functions specifically designed for meta-analysis, such as meta and metaphor. While using R for meta-analysis requires coding skill, it offers greater flexibility and customization option. Moreover, R is free and has a large and active user community, which means there are numerous online resources and tutorials available to support users. Finally, Stata is a comprehensive statistical software package widely used in various fields of research. It offers built-in commands and modules for meta-analysis, such as metan and meta-reg. Stata provides a user-friendly interface for data management, analysis, and visualization. However, it is a commercial software that requires a license, which can be relatively expensive. Similar to R, Stata also requires users to have some coding skills to conduct meta-analysis. So as we have mentioned before, many researchers and organizations have created videos tutorials on using Riefman for meta-analysis. This tutorial can help users, especially those new to Riefman, navigate through the software and understand its functionalities. We highly recommend you to watch those helpful tutorials on your own to gain a better understanding on how to use Riefman. Most meta-analysis utilize forest plots to display the result of pooling multiple studies. A forest plot provides a visual summary of the effect size and confidence intervals of each individual study, as well as the combined effect estimate at the bottom of the forest plot, as shown on the slide. So, how do we interpret a forest plot? So first of all, the forest plot consists of a vertical line, also known as the null effect line or the line of no effect. This line represents the point where the treatment or intervention being studied has no effect. Each study included in the meta-analysis is represented by a horizontal line called a study marker or square. The position of the square on the horizontal axis represents the estimate of the treatment effect or outcome measure for that study. The length of the horizontal line represents the confidence interval around the estimates of the treatment effect. A longer line indicates a wider confidence interval, which means more uncertainty in the estimated effect size. The diamond-shaped symbol at the bottom of the plot represents the combined effect estimate, also known as the pool effect size or summary estimate. It summarizes the overall effect size across all the studies included in the meta-analysis. The width of the diamond represents the confidence interval around the pool effect estimate. A wider diamond indicates more uncertainty in the overall estimate. Okay, so next, the test for overall effect and p-value at the bottom of the forest plot indicates whether the overall effect is significant or not. So as usual, a p-value less than or equal to 0.05 denotes statistical significance. Another way to determine if the overall effect is significant is to visually examine whether the diamond crosses the null effect line. If the diamond crosses the null effect line, the overall effect is not significant and vice versa. So in this example shown on the slide, there is significantly lower risk of post-op 30 days complication in robotic compared to laparoscopic surgery, with a risk ratio of 0.78, with a confidence interval between 0.61 to 0.99. The p-value is 0.04, which denotes statistical significance. And this is further confirmed on visual inspection of the diamond, which does not cross the null effect line. So, when you collect data for data meta-analysis, it's important to consider the type of outcome being studied. For dichotomous outcomes such as proportion, incidence, or prevalence, the key data to collect includes the event rate, like the number of events, and the total sample size. Other measures to be collected include odds ratio, risk ratio, or hazard ratio. But when it comes to continuous outcome, the key data to collect includes mean and standard deviation for each study. However, in some studies, they can report medians and interquartile ranges. This information can still be collected to estimate the mean and standard deviation following established methods proposed by previous researchers. So this allows for the inclusion of studies that they are reporting medians in their study as well. Okay, so for example, in a meta-analysis that examines proportion, such as prevalence or rates, the unit of analysis typically focuses on individual events contributing to these measures. So let's consider an example of the prevalence of thyroid eye disease in Graves' disease. In this case, the numerator represents the number of patients with thyroid eye disease, while the denominator represents the total number of patients with Graves' disease. By pooling these individual events across multiple studies, the overall prevalence of thyroid eye disease can be estimated. So prevalence meta-analysis is often considered as a single-arm analysis, since there are no arms of comparison involved. However, in some cases, estimating prevalence is part of a broader meta-analysis that investigates various aspects such as risk factor and outcome related to a specific condition. For conducting meta-analysis of single-arm study, the R command metaprop can be utilized. The command is available within the meta package, which provides tools for pooling and analyzing proportion in meta-analysis. Before we move on, do you know what's the difference between prevalence and incidence? And are these terms interchangeable? While the terms prevalence and incidence are largely interchangeable, it's important to note their difference. Incidence refers to the number of new cases of a particular condition or event that occur within a defined population over a specific period of time. It measures the rate at which new cases of the condition develop and help us understand the risk of developing the condition in a population. Prevalence, on the other hand, represents the proportion or percentage of individuals in a population who have a specific condition at a given point in time or within a specific time period. It includes both new and existing cases of the condition and provides us with the understanding of the burden of the condition in the population. So now that we've clarified these important two terms, let us move on to dichotomous outcomes for double-arm studies. When analyzing double-arm study that involve a control and a comparison group, there are two distinct approaches for data collection and analysis. In the first approach, raw data is collected and pooled. For instance, when calculating the risk of developing thyroid eye disease in patients with Graves' disease compared to those without Graves' disease, the data to be collected includes the number of TED cases among patients with Graves' disease, the total number of patients with Graves' disease, the number of TED cases among patients without Graves' disease, and the total number of patients without Graves' disease. To analyze this data, the meta-bin command within the meta package can be used. The second approach involves collecting and pooling the reported odds ratios, risk ratios, or hazard ratios from the included study. In this case, it is crucial to extract the maximally adjusted estimate and make note of the adjustment made in each study, as this information should be reported in the final manuscript. The meta-gen command, also available within the meta package in R, is suitable for analyzing this type of pool estimates. So the choice of approach depends on what data is available in the included study, as well as what are the outcome of interest. And before we move on, just another question. Do you know what is the difference between odds ratio and risk ratio? So before we reveal the answer to the question, these are just some example of forward plots generated using the meta-bean and meta-gen command in the R software respectively. For the pool risk ratio of post-operative complication in robotic versus laparoscopic surgery, the raw data was collected and pooled using meta-bean in approach as shown in approach 1. In comparison, the hazard ratio of cardiovascular event in liver transplant recipient with or without metabolic syndrome was extracted directly from the included study. This was then converted to treatment estimate and standard error using pre-specified formulas and pool using the meta-gen command, shown in approach 2. Alright, so now let's get back to the difference between risk ratio and odds ratio. While they both estimate the relative risk of an event, they have very different interpretation and are used in different situations. So a 2x2 grid is useful in understanding the differences. So the risk ratio, also known as relative risk, compare the risk of an event occurring in experimental group to the risk in comparator group. The odds ratio, on the other hand, estimates the odds of an event occurring in one group compared to the odds of the event occurring in another group. Unlike the risk ratio, which measures the risk directly, the odds ratio measures the odds or probability in an event. The odds of an event represent the likelihood of the event occurring compared to the likelihood of the event not occurring. So how do we interpret them? So let's look at risk ratio first. So a risk ratio of 3 indicates the risk of experiencing complication within 30 days after robotic surgery is 3 times higher compared to laparoscopic surgery. In percentage terms, this translates to a 200% increased likelihood of complication in robotic surgery compared to laparoscopic surgery. So to present the increase in percentage, we can use the formula 100% times RR minus 1. On the other hand, the odds ratio of 3 suggests the odds of developing complication within 30 days after robotic surgery are 3 times higher compared to laparoscopic surgery. Worth noting, odds ratio cannot be expressed as percentage increase. So in summary, odds ratios are often challenging to comprehend and apply in practical setting. They are frequently misinterpreted as risk ratio, which can lead to confusion and incorrect conclusion. Risk ratios are more intuitive and easier to understand in terms of their practical implication. So it's therefore recommended to use risk ratio instead of odds ratios whenever possible. Next, we'll move on to continuous outcome. So continuous outcomes refer to variables that can take on any value within a certain range, such as age, weight, blood pressure, or scores. So this can be used to calculate mean difference or standardized mean difference. So what is the difference between the two of them? While mean difference represents the absolute difference in means between two groups or intervention being compared, it's calculated by subtracting the mean of one group from the mean of another group. So mean difference is commonly used when the continuous outcome across studies are measured using the same metric. On the other hand, standardized mean difference is used when the outcome measures are on different scales or have different units of measurement. For example, one study may measure their blood pressure in millimeters of mercury, while another study may report blood pressure in kilopascal. Alternatively, one study may use a self-report questionnaire, while another study may use a clinical assessment tool. Since the measurement scales differ, it becomes challenging to directly compare the mean differences across studies. In such situations, SMD, standardized mean difference, is used to standardize the mean differences and allow for meaningful comparison. To analyze this data, both mean and standardized deviation are needed, and the meta-con command within the meta package in R can be used. And as shown, this is an example of a forest plot showing the mean difference in length of hospital stay for patients undergoing laparoscopic versus robotic surgery. However, sometimes we can run into problem when we are doing a meta-analysis. So what happens when the study report result in other formats? For example, studies that report medians with ranges or interquartile ranges, or means with 95% confidence intervals. Well, we can always convert them using suitable formula. When dealing with studies that report medians along with ranges or IQR, a suggested approach is to utilize the formulas outlined by Wan et al. These formulas provide an estimation of the mean and standard deviation, which can then be used in the meta-analysis. On the other hand, for studies reporting means along with confidence intervals, it is recommended to employ the formulas proposed in the Cochrane handbook. Okay, so now let's move on to the choice of statistical model. So as mentioned before, it is generally recommended to use random effects model rather than fixed effects model. This is because random effects model is widely accepted and considered appropriate for most meta-analysis, as it accounts for both within study and between study variability, providing a more conservative and generalizable estimate of the overall effect size. The random effect model is also the default mode in software such as Riefman. Okay, so now we can move on to subgroup and sensitivity analysis. So there are just two distinct approaches used in meta-analysis to explore the robustness and variability of the result. So first, let's look at subgroup analysis. It examines the effect of an intervention or exposure within specific subgroups of the study population. And what it aims to do is to determine whether the intervention's effectiveness differ across various subgroups based on certain characteristic or variable. This characteristic can be age, gender, disease severity, baseline race, or other relevant factors. In the example on the left, subgroup analysis can be conducted for study using oral biphosphonate and study using IV biphosphonate. If a particular study gave both oral and IV biphosphonate to the patient, the study should be excluded from the subgroup analysis. In contrast, sensitivity analysis is performed to assess the robustness of the result by systematically varying different aspects of the analysis. By conducting sensitivity analysis, researchers can explore the potential source of heterogeneity or bias in the meta-analysis. In the example on the right, there is a well-established association between female gender and depression in the general population. It is of interest to investigate whether this association holds true for liver transplant recipients. Thus, a sensitivity analysis can be conducted to calculate the prevalence of depression in female liver transplant recipients only. So let us look at some example now. So based on the overall pool analysis, the risk of post-op morbidity in conventional versus fast-track surgery is not significantly different, as evidenced by p-value of 0.73 and confirmed on visual inspection as the diamond crossed the line of no effect. However, the test for subgroup differences shows significant difference. This indicates there is significant difference between open surgery and laparoscopic subgroup. Besides looking at the p-value for subgroup difference, it's also important to examine if the confidence interval of the two subgroups overlaps. If the two confidence intervals overlap significantly, the two subgroups are unlikely to be significantly different from one another. So over here, the two confidence intervals, as evidenced by the two diamonds, only overlap slightly, so the difference between both can still be statistically significant. Now let's take a closer look at each subgroup, namely the open surgery group and the laparoscopic group. The risk of post-op morbidity in the open surgery subgroup is not significantly different, as evidenced by the p-value of 0.23. In contrast, the risk of post-morbidity in the conventional group is significantly higher than fast-track surgery among the laparoscopy subgroup, as evidenced by p-value of 0.03. However, do note that if the overall pool analysis is not significant, as in this case, then it will be likely that any significant result that arose from the subgroup analysis will be likely to be due to chance. as a subgroup analysis will be based on even smaller number, it could have a weaker power to detect the difference. Okay, and understand all this information are quite overwhelming. So we are looking at the last section before we go through some examples. So now we'll just be looking at meta-regression. So meta-regression is a statistical technique used in meta-analysis to explore the relationship between study-level characteristics and the effect sizes reported in the included studies. It allows researchers to investigate whether certain factors, such as age, BMI, or publication year, have an impact on the overall effect estimate. In meta-regression, the effect sizes from each study are treated as dependent variables, while the study-level characteristics are treated as independent variables. The relationship between these variables is then analyzed using regression analysis. So there are a few terms that we have to achieve before running a meta-regression. At least 10 studies are required before we can move on to a meta-regression. And the result of a meta-regression can be presented as a bubble plot. And there are two options for conducting meta-regression or R. And the most commonly used is meta-reg command, which can be found in the meta package. Meta-reg is typically used for double-on studies. In comparison, generalized linear model, which can be found in the survey package, is a more flexible type of regression, which can be used for single-arm analysis. Okay, so I think we have gone through a lot of concept of statistical analysis in meta-analysis, and understand those information can be overwhelming. So let us just be looking at some examples to consolidate our knowledge. So first of all, let's look at the first example. So this example demonstrates meta-regression using MELD score on an overall survival in NASH versus non-NASH patients. So the regression coefficient or beta coefficient obtained for a meta-regression analysis will describe how the outcome variable changes with a unit increase in the dependent variable. The statistical significance of the regression coefficient is a test of whether there is a linear relationship between the intervention effect and the explanatory variable. So result of our meta-regression here actually reveals that higher MELD score was associated with significantly worse overall survival in NASH compared to non-NASH etiology. Okay, so let's give it a try. What we can now do is try to pause the video and answer these questions by interpreting the plot yourself. And what you can do is you can pause the video for a minute or two. Try to write down your answer on a piece of paper, and we will just be talking about this answer in a bit. Okay, so as usual, I assume everyone has gone through the questions, and now we just be discussing about the answer. So the dependent variable in this case is in-hospital all-cause mortality, while the independent variable is the proportion of males. The bubble plot reveals that male gender did not have any significant effect on in-hospital all-cause mortality. Okay, so as great as a meta-regression sound, there are still some limitations. It's important to note that any significant association observed may be observational in nature and potentially confounded by various factors. And another limitation is the potential for aggregation bias. So this occurs because meta-regression relies on means or medians of patient characteristics obtained from each study. Aggregating data in this way can introduce inaccuracies, as the individual patient level data are not directly considered. Therefore, while meta-regression can provide valuable insights into the potential influence of covariate on the effect size, it is important to interpret the findings cautiously. Alright, so I believe we have provided quite a nice overview of statistical methods in meta-analysis, and it's a lot to digest, and the best way is always by practicing it. So in addition to the fundamental components of a meta-analysis that we have covered, there's actually a lot more advanced technique in the field that can be explored in our advanced courses. So for example, our courses will just be looking, other than the traditional meta-analysis, we will also be talking about advanced technique like network meta-analysis, individual patient data meta-analysis, Bayesian Meta-Analysis, diagnostic test accuracy meta-analysis, and many others. So hopefully we'll see you in our advanced meta-analysis courses, which we will be releasing soon. So this concludes our episode for today, and we have covered quite a wide range of statistical methods for systematic review and meta-analysis. So as always, thank you for watching, and in our next video we'll be covering how to write, interpret, and present results in your manuscript. Hope you enjoyed the episode today, and Research Lab X is here to help you to find the answers you need. We have a unique approach to research that emphasizes collaboration, creativity, and innovation. Our team is available to provide guidance and feedback throughout the process. If you are interested in learning more, contact us at Research Lab X today using the link shown. Thank you.